Okay, so this unit is rotation. This is another transformation. Let me lighten this. Let me lower. This is another transformation. Now, um, we know rotation like the Earth rotates around the sun, and we know that path is an ellipse. It's not a circle. In this class in math, the idea of rotation is that there's a fixed point. We're going to call that C, and it has an orbit or a circular orbit around it. Okay, and the idea is that point P, so point P gets transformed to P prime through a rotation, little r. I think for reflections I use little r. Some textbooks use little r. This textbook use big R for reflections, little r for rotation. The idea is there's a center and a specific rotation. So moving around the circle is a rotation by angle. And that's the idea. That's the idea of transformation, is that a point, there's a center with a circular orbit around it, and a point is moving around it. That's the idea of rotation in this class. So what's the idea behind a rotation? The idea is that there's a center, there's a point, and then the point is rotated. So the idea is P is rotated to P prime. It's not reflected. It might be. It's not translated. It might be. We want to know the rules to say, oh, it actually was rotated. First of all, CP has to be congruent to CP prime. And also, angle P prime CP is equal to theta. And that's the idea, and that's how we show that P has been rotated to P prime about C by theta degrees. That's the strict definition of rotation. Now, in this class, you're going to only rotate about the origin, and your theta is going to be 90, 180, 270, and 360. And it's kind of, actually, you can prove that. We can prove these. I'm just going to give you the rules right now. So, if we take a point, xy, and we rotate it 90 degrees, what do you think? Well, the rule is it becomes negative y, comma x. Flip it and negate. That's not a coincidence. If we take xy and we rotate it about the origin 180 degrees, once again, flip it and negate again. Negative x, negative y. If we take 180 xy and rotate it 270 degrees, flip it and negate again, y, negative x. And then finally, if we take a point and do a full 360 degrees, it takes us back to xy. So it's kind of like the identity. It's kind of like adding 0 or multiplying by 1. So these are the rules you should know. This is the definition of reflection. We can actually prove this. I think we did prove it in one of the other. No, I proved it in another class. We can prove it in this class. Let's say that we have our center is 0, 0, right? I have my xy, and I'm rotating it 90 degrees, right? And the question is, what is this point here? This is CD. And so what's going on? Well, let's see, if we drop this here, we have, this is y, this is x. So what's happening here? What do you think? Well, any ideas? What do you think? Let's see. This is beta, this is alpha, that means this is alpha. This is 90 degrees. That means this is beta. If we drop in altitude, this is alpha. That means this is a right triangle. That means these triangles are similar. Are they similar? Well, not only are they similar, they're congruent because this is the radii of a circle. Once again, this circle right here, this becomes x, and this part here, this becomes y. So the question is, what are these coordinates? Well, the height, this is the x, this is negative y, and hence we just proved that when you reflect x comma y 90 degrees, the result is negative yx. Once again, I took my point and I rotated it 90 degrees. I dropped my triangle and I got my triangle here. This was the coordinate xy. The base was x. The height was y. Therefore, and I kind of put in dummy variables, alpha, beta, because this is the first quadrant. This is 90 degrees. Therefore, this is alpha. This was a 90-degree rotation. That means this angle here is beta. This is alpha. That's beta up there. We have two triangles that are similar, but because this was part of the unit circle, right? The radius is equal. The triangles are congruent, and therefore we matched up the sides, and we found that the height is x, and the length on the y-axis, on the x-axis, it's y. But remember, it's going in the left direction, so this would be like -3. So that's negative y, and that's the answer. So try these problems. So for example, you might say, rotate. Oh, sorry. So you might see, 2, 3 after a rotation of 90 degrees. You go, -3, 2. You might see a rotation of 180 degrees. Of 5, -1. Well, you can either memorize that, you can flip it and negate. Flip it and negate. You can remember with 180 degrees, both of these get negated. Kind of interesting to think about that. And then the last example. So I told you that we're always rotating around the origin, but let's say I gave you a trick question. I said, I want you to rotate 90 degrees around about the point 1, 2, the point 5, 3. So you just, Mr. Ellie, you just told you we're always doing it at the origin. Well, what do you think? Well, please remember that rotation is also a rigid motion. It's also a rigid motion. So the transformation doesn't change, it's not going to change the area of the triangle. Like we saw that in that diagram over there. The triangle, it created a congruent triangle. Changed its position, but it didn't change the area, the length. So what I'm going to do is I'm going to shift everything back to the origin. So I'm going to transform -1, -2. So now I have a rotation of 90 degrees at the origin, but my point is going to be 4, 1, okay? Then, which results in -1, 4, and then finally, I'm going to push everything, bring it back. So I did my rotation. It's like I moved my circle down to the center. I did my rotation, and I'm going to move the whole thing up, over 1, up 2. Finally, a transformation back, 1, 2, of the point -1, 4, which results in the final answer, 0, 6. Kind of interesting. Yeah, I think that's kind of interesting. Yeah. Nice. Okay. Good luck.